Okay then, as you can see in my notes, we're up to page 22. The last topic we looked at was Taylor series and stationary points. So we are ready to start the integration section. But just before we move on, before we move on to integration, I want to just do a little bit more explanation about the stationary points. Okay, so we need to explain the classification of stationary points. Stationary points of a surface. So now what I'm talking about here is using the Hessian determinant. So this was how, when we found the stationary points to a function, how we classified them into minimum, maximum, or a saddle point. So the Hessian determinant was this quantity d, which was the product of the two second-order partial derivatives d2f dx squared and d2f dy squared minus the square of the mixed second-order partial derivative. And just to remind you of the classification, if d was less than 0, this implied a saddle point. If d was greater than 0 and d2f dx squared was less than 0, that implied a maximum point. And if it was the other way around, if d was greater than 0 and d2f dx squared was greater than 0, then it was a minimum point. Okay. So this was how a stationary point was classified. So you have this mixture of second-order partial derivatives d, the Hessian determinant, and you evaluate it at the stationary point. This expression is a function in x and y. When you evaluate it at the stationary point, you get a numerical value. If it's negative, you got a saddle point. If it's positive, you then check the second-order partial derivative d2f dx squared, and whether that is positive or negative then determines a maximum or minimum point.
Why does it only take account second-order partial derivative of
x? Well, it will also work if you use the y. Yeah, so why is it the x derivative being used here as opposed to the y derivative? Well, it would also work with the y derivative. You can use either. That'll become apparent after I've given the explanation here. You can see how it is that comes about. So basically, the question is why? Why is it that way? And it's so we need to explain this, but it also makes use of Taylor series, or the idea of Taylor series. So what we'll do is we'll let AB be a stationary point of our function f of xy. So what that means is, i.e. df dx and df dy are both equal to 0 at the point AB. When you evaluate the two first-order partial derivatives at AB, they're both equal to 0. Okay, that's how we find the stationary points. They're the solutions. And that we can understand because the first-order partial derivative tells you the slope of the surface in the x direction or the y direction at that point. So if both slopes are 0, that means the tangent plane is exactly horizontal. So it's going to be one of these stationary points, a minimum, maximum, or a saddle point. The type of stationary point it is, i.e. minimum, maximum, or saddle, can be judged from the behavior of, well, what? Well, of how the value changes. So delta f, when you look at the function f evaluated at a nearby point, so a plus h, b plus k, and compare that with how it behaved at ab. And we recognize that kind of construction. This is the delta f. So looking at the value of the function at a point which is nearby to the stationary point AB that we found. So the new x coordinate is a plus a little bit h, and the new y coordinate is b plus a little bit k. Now here's where we're going to make use of the Taylor series. We're going to use the Taylor series. Remember, the Taylor series tells you how to think about this value of the function at a point a plus h, b plus k, which is close to a base point AB. So the Taylor series tells us that this change in value, and it's a change in value we need to see. So when we analyze this, if we see that the change in value is always positive, so no matter what the h and k, for any values of h and k, if the function always increases, that means the base point must be a minimum. Yeah. So if you move away from the base point in any direction, if the value always gets bigger, that means you're at a minimum. If the value always gets smaller, so if the change is negative, then that must mean you're at a maximum at AB. And if it's a mixture of behavior, if for some values of h and k, when you move away from the base point, you're going up in value, and for other values of h and k, you're going down in value, then it's a mixture of the two. So that will be the saddle. Okay. And we can get a handle on this and how the second order partial derivatives play a role by looking at the Taylor series. Okay. So we're going to take the Taylor series for the function f applied to a plus h and b plus k. Now remember, the expression for the Taylor series was, first of all, you had the term f of ab. Then you had some terms depending on the first order partial derivatives. But we know that they're zero, and we're subtracting f of ab here. So the first things that are going to appear in this expression delta f are going to be the second order partial derivatives. So you're going to have your h squared d2f dx squared. You're going to have your k squared d2f dy squared. And you're going to have your 2hk d2f dx dy. Plus these higher order terms in h and k. So this is the 1 over 2 factorial times the square of that differential operator from the Taylor series. Now it's enough to focus. So I've left out the beginning, the constant term from the Taylor series because that's subtracted here, and I've left out the terms that depend on h and k to the power 1 because their coefficients are the partial derivatives, but they're equal to 0. So the first terms that appear are these ones.
Why is it 1 over 2 factorial?
Well, because that's part of the Taylor series formula. This 1 over 2 factorial. Remember, in the Taylor series formula was this expression here. You had the 1 over n factorial. So that's the 1 over 2 factorial.
Okay.
Now, when we're investigating this and we're trying to find out what type of stationary point it is, all we're really interested in doing is judging the sign of delta f, whether it's a positive or negative quantity for various values of h and k. Okay. So I'm not so interested in the particular value of this thing, but just rather being able to judge the sign of it. Okay, so I'm going to say this is equal to, but we're just talking about the sign. So the sign this will have, I can forget about the factor of a half, because the factor of a half doesn't affect the sign of anything. So I'll leave that off. And I'm going to start working on this expression, and I'm going to divide out by the second order derivative, 1 over d2f dx squared. Okay, so I'm going to have a 1 over that second order derivative there. And so to compensate for that, I'll have to multiply everything through by d2f dx squared. So I've already got d2f dx squared here, multiplying h squared. So that will change to the square of d2f dx squared. And here I'll have k squared d2f dy squared d2f dx squared. And then here I'll have plus 2hk d2f dx dy d2f dx squared. And I can forget about the higher order terms in h and k as long as I regard that this expression is applying for small h and k. See, these higher order terms in h and k will have order at least 3, h cubes, k cubes, and so on. So as long as h and k are small, the behavior of this whole expression delta f will be dominated by these low order terms. So as long as h and k are small, as long as they're small, I'll know that the sign of delta f is going to be given by this expression here. Okay. So what I've done here is I've forgotten about the higher order terms in h and k. Because for small h and k, it'll be dominated by these lower order terms. And to start working on this expression and to draw out the Hessian determinant, I've begun by dividing everything by 1 over d2f dx squared. So to compensate for pulling this out of the front, I got to multiply that whole bracket by d2f dx squared. So I get d2f dx squared plus d2f dy squared by d2f dx squared plus my 2hk d2f dx dy multiplied by d2f dx squared. Now what we're doing here is it's kind of a completing the square argument. So we're trying to draw out as much as possible squares in this expression. Squares we know are always positive. So that'll help us judge the sign of the resulting thing. Okay. So this is going to have, this is equal to, so I've still got my d2f dx squared here. And when we look at these things in the brackets, it kind of, a little bit of it looks like the square of a certain quantity. Okay, if I look at the first term here, so this is the square of something. This first term here is the square of h times d2f dx squared. And here I've got the product of h d2f dx squared with d2f dx dy times k. And so I can make use of that. So I can say this is h times d2f dx squared plus k times d2f dx dy, all of it squared. But then I got to make some corrections. So the corrections, see, this will, when I square this bracket, it generates some of these.
generates the h squared square of d2f dx squared. It generates the 2 times the product of this with this, which I see at the back here. But it doesn't generate this thing, nor does it generate, it doesn't generate this term, and it also generates something which isn't there, which is k squared times the square of d2f dx dy.
So I still got this object here. So I still got k squared d2f dy squared d2f dx squared. And I also generate k squared times the square of this, which isn't up here, so I must subtract it again. Minus k squared d2f dx dy, all of it squared. And what we see, so is everybody clear on this? So we got to this stage here. We've noticed that it's the square of this quantity that generates the first and the third term. Doesn't generate this middle term, so I still need that here. And it also generates k squared times the square of this, which isn't up there, so I must subtract it. Now you see I've got a factor of k squared there in both terms. So that's k squared into, and it's k squared into the Hessian determinant. So it's d2f dx squared, d2f dy squared, minus the square of d2f dx dy. So that quantity there is the Hessian determinant. And so now I'm going to consider the sign of this. So the sign, so positive or negative, of all this. So the simplest case, notice I haven't bothered to reproduce this inside the bracket because I'm not really interested in it now. I'm just interested in the fact it's a square. So squares are always non-negative, of course. So this is the Hessian determinant D. If D is positive, right, then inside the large bracket here, everything's positive, or non-negative at least, right? Because you've got the square of something plus the square of something times something positive, okay? So if the Hessian determinant part is positive, then this whole bracket here is positive, and it's multiplied by the reciprocal of d2f dx squared. So the sign of this whole thing will be equal to whatever the sign of this is, okay? Because it's this thing multiplied by something positive. So what sign it is, whether it's positive or negative, just comes down to the sign of this, okay? So when you examine everything else, you see it's a square of something, non-negative, square of something, non-negative, multiplied by something which, if it's positive, the whole big bracket is going to be non-negative. So the sign of the whole expression will come down to the sign of this object here. So if the Hessian determinant, this part here, is a positive quantity, then the sign of delta F, at least for small h and k, is the same as the sign of d2f dx squared. Okay, because it's sitting out here at the front, or it's reciprocal, but reciprocal doesn't change the sign of something. It's sitting out here at the front, multiplying some kind of non-negative number. So if this is positive, then delta F is positive for small h and k. Delta F, remember, delta F is the difference between the value of F at a nearby point minus the value of F at the stationary point. So if delta F is always positive, it means the value of F at the nearby point is always greater than the value of F at the stationary point, so therefore it's a minimum. i.e., AB is a minimum. And if d2f dx squared is less than 0, then delta F is less than 0, i.e., the stationary point is a maximum. So we're still within this assumption that the Hessian determinant is positive. Okay. So if delta F is negative, it means the value of F at the nearby point is smaller than the value it had at the base point. So if you move away from the base point and you always get smaller, it means you're always coming down the surface. So it means the base point is a maximum point. So the other case then is if the Hessian determinant is negative. So then what's the sign of this quantity if the Hessian determinant is negative? So what's the sign of all of this if this part here is negative? Well, we've got 1 over d2f dx squared. Okay, that will have a positive or negative sign. It's multiplied by this large bracket. The large bracket is a square of something, which is non-negative, plus k squared, which is non-negative, multiplied by something negative. So inside the large bracket, we see a non-negative plus a negative. So we're unsure. So it's a positive quantity minus a positive quantity. So what the sign of this whole bracket is depends on how big this one is compared to this one. So we're unsure. And then it's multiplied by the reciprocal of this, and we don't necessarily know what the sign of that is. Okay. So if the Hessian determinant comes out as negative, we can't make a judgment on what the sign of this whole thing is. It depends on the relative sizes. So it's going to depend on the size of h and k and the particular values of these second order partial derivatives. Okay. So if d is less than 0, the sign of delta F is unclear and will depend variously on h, k, the signs of these quantities, and the magnitudes of these quantities, and the second order partial derivatives. So delta F is positive sometimes, negative other times. So it's a mixed picture. So that's the saddle point. Yeah? The saddle point is a stationary point where you go off in some directions, the surface is falling away. You go off in other directions, the surface is rising up. Okay, so it's a mixed picture. So i.e. a saddle point. We know it's a stationary point because the two first order partial derivatives have vanished at AB. So the tangent plane is flat, but we're uncertain precisely. Or it's just the sign of delta F depends on these various quantities. So for some directions and some values, it's going to be positive. For other values, it's going to be negative. So that's your saddle. Okay. So that's a nice way of tying the two things together, showing how the concept of the Taylor series, which allowed us to approximate the change in value of the function f at a nearby point to the stationary point, approximate it by only considering the second order terms. And the sign of delta f will then be the sign of whatever this expression is, at least for small h and k. We're only focusing on the sign of it so we can forget about the half. And then we hammer away at that expression there a bit to bring out the presence of the Hessian determinant and structure the thing in terms of squares so we can then kind of try and get a handle on the sign. Okay? So you know a square is always non-negative, and so you can try and judge the sign of the whole thing with reference to that. Okay? So that, I mean, it's not a completely rigorous from the ground up proof of the thing, but it's a pretty strong argument that explains why the classification scheme for stationary points is as it is. Okay. So hopefully that will inform your use of it and help you to understand it, and well, you know, takes away the mystery or just the voice of authority. Actually see now why it is that way. Okay. So it's at 12:44 now. So I think I won't blast into the integration section and try and do a lot of integration in 5 minutes. So next week, when I see you, we'll have 2 lectures next week. We'll make a good start on the integration sections, get ourselves up to the situation where we can bring in exercises 1.5. So for our tutorial, for the upcoming tutorials in this, just keep working on the tutorial exercises in 1.4. Begin work on the coursework. Certainly, any queries you might have about the coursework, do feel free to approach me or your tutor about them, just to see if there's any clarification they can give you on it. Okay? Okay, so we'll finish there for today. If you've got any extra questions, I'll stick around for 5 minutes or so. Feel free to come up.